So, as Carol mentioned, my name's Brian Campbell, and I'm a NASA Senior Earth Science Outreach Specialist with the NASA Wallops Flight Facility, which is a field office of the NASA Goddard Space Flight Center that's based in Greenbelt, Maryland. But my office and lab are actually in Wallops Island, Virginia. I've only been to my lab 3 times and my office 3 times since the beginning of the pandemic last March. So yeah, so I kind of miss it. But I live in Salisbury, Maryland, so I live about 55 miles from Wallops. And I often get the words from people that, oh, you drive 55 miles, you drive an hour each way every day to work. And I say, well, you don't understand. I said, there's no traffic here on the Eastern Shore in these areas. Going through Princess Anne and Pocomoke City, and there's no traffic at all. When I lived in the DC Baltimore region, I lived in Greenbelt and I lived in Severn. And when I lived in Severn, Maryland, it's from my house to Severn, sorry, my house in Severn to the Goddard Space Flight Center was 12 miles as the crow flies, but it took me an hour and 15 minutes to get there and back each day. So each direction was an hour and 15 minutes to go about, on the road, was probably about 17 miles, but, an hour and 15 minutes each way. So I don't miss the traffic, and all that. I do go to DC often, and I go to larger cities often when travel is, when travel was a thing, hopefully in the near future. But yeah, so what I do at NASA, and you'll learn a lot about that today, but I'm in my 20th year at NASA. I was actually a high school science teacher in Cambridge, Maryland for 4 years in the late 90s, early 2000s, just after, getting out of graduate school from the University of Pittsburgh. And I started off in the earth sciences and remain in the NASA earth sciences. And what I do is I do a combination of things. I do the science, but what I do with the science is, through the analysis of it, I communicate it. So I make it understandable for audiences all over the world, literally all over the world. And you'll see some things that I'm going to mention today, something called the GLOBE program. It's a Global Learning and Observations to Benefit the Environment program. And it's a program that was started in 1995 and was basically a brainchild of Al Gore 26 years ago. And it's a grouping of students, educators, citizen scientists, and researchers from 125 countries now. We just had the last country join in. It was, when did they join in? Maybe 3 weeks ago. It was a country of Bhutan, and they just joined the GLOBE program. And the GLOBE program is really unique because it's a NASA-funded program, but it's also supported by NOAA, the National Science Foundation, and the U.S. State Department. And it actually requires basically a country-to-country agreement to become part of the GLOBE program, because we're sharing data and observations and all these things, so of scientific importance. So, and I apologize for my cracking voice because I've given so many talks over the last couple weeks, because, Earth Day is April 22nd, but at NASA, Earth Day becomes Earth Month, and sometimes Earth Month 1.5, So we've been doing presentations and planning for, Earth Day for literally the entire year so far, and the end of last year. So I've given, this is probably like my 5th talk this week, and I have a bunch next week and the following week. So, when you're in earth science, you get out there and talk a lot about earth science. But what I do, I work a lot with NASA Earth observing missions. And a lot of these NASA Earth observing missions are called the NASA fleet. This is an Earth observing fleet when you look at just at the planet here on the left side. And all these names and acronyms that you see surrounding the Earth, these are all active missions in the earth sciences. The ones you see in green, okay? The ones you see in orange are actually earth science missions, but they have a biological and physical capabilities. They look at biological and physical variables. And what you see going around the earth are actually satellites that are in space and, basically looking down at the planet as they're moving around the planet at speeds of like 15 to 17,000 miles an hour. And they do different things. They're looking at the planet's soil moisture. They're looking at the tree canopy, which we'll talk about a lot today. But then we're also looking at the oceans and the landforms and, the building of cities, deforestation, lots of different things, atmospheric carbon, the carbon sequestration on the ground. So lots of different things here. And I have one circle there called ICET-2, and it's a satellite mission that I've been working on for the last 10 years. Well, actually, now it's been 12 years. We launched the satellite in 2018, and I'll go through that in a second. But what you're also seeing on the Earth here, you see the International Space Station. You see that that path that goes around the Earth. The International Space Station houses a lot of instrumentation that actually is vital for us understanding our planet. Because as you know, our planet changes over time. And we really have to focus on what our planet looked like in the past, what it looks like in the present, in order to understand what is going to happen in the future to our dynamic planet. So there's lots of variables here, but all these, I like to think of each one of these satellites as part of a jigsaw puzzle. It's a jigsaw puzzle of understanding our planet and our changing climate. And each one of these plays a vital role. And ICET-2 is probably the most advanced technological satellite in space right now. And you'll understand why that is in a second. But then what you're also seeing on this image, you're seeing Mars, because a lot of people think Mars is analogous to the Earth. That at one time Mars may have looked like the Earth or something like it at one time. So a lot of the work that we do on Mars, the stuff with the recent the rover, Perseverance, we had Curiosity and Opportunity and Spirit rovers in the past. And they all, are doing great things trying to figure out what the heck that planet is actually about. What is on there? Was there life at one time? Was there, liquid water? We know at the poles there's frozen substance, and it's primarily frozen carbon dioxide. But we want to try to figure out, what are the similarities between the Martian surface and Earth's surface? And the only way we can do that is to know what's happening on our planet in order to compare it to what's happening on Mars. So I just wanted to show you this because I've been working with a lot of missions over the last 2 decades at NASA. I've worked with, as I mentioned, ICET-2 now. I work with GPM, the Global Precipitation Measurement Mission. I work with the SMAP mission, which is Soil Moisture Active Passive. It's a satellite that's able to measure the planet soil moisture, the entire planet's soil moisture every 3 days. So it's just an amazing satellite. And a lot of these satellites that I just mentioned is we have some type of components at the NASA Wallops Flight Facility, meaning that before SMAP went up, they flew the same instrumentation. Basically, it's called an active radar and a passive radiometer. And they basically look at the soil moisture that is in the soil to about 5 centimeters below the surface. That's kind of the gold standard for looking at soil moisture. And you guys are all master gardeners, and so you understand the whole soil moisture thing, and the root structure and how far the roots go down in different tree species and plant species and shrub species. All different vegetation have different root structures, but we see those most vital nutrients and moisture in that top 5 centimeters. Yeah, yes, it does go down further, but that's kind of that, as I mentioned, the gold standard for understanding, say in an ecosystem, where all those nutrients are in the soil. In the rainforest, that top 5 centimeters are basically about 2 inches. And a lot of this stuff here that we do at NASA, before we launch these big satellites into space, we do test flights. We put instrumentations on aircraft and out on boats, and we actually have scientists who have gone to Antarctica and Greenland and have taken measurements of how thick the ice is using like ground penetrating radar to figure out what they need to do as far as figuring out elevation for the ICET-2 mission. And how do we figure out how tall something is on the planet when a satellite is flying from 300 miles above the Earth? How do we do that? So we're going to get all into that in a little bit, with ICET-2, and then ICET-2 is going to lead us into why NASA cares about looking at trees and tree height, and that's why we're here today, right? We're interested in trees and tree height. Trees are a huge thing right now all over the planet. People are having these huge tree planting campaigns. We know they're good for, pulling out the pollutant carbon dioxide out of the atmosphere. We know that they're good for helping to cool the planet. They are great for, photosynthesizing and, converting that carbon with the sun's energy and nutrients and converting that into our breathable oxygen, right? So, trees are so vital, but, a lot of times you look at a tree and you see a tree outside. I'm looking outside, on our side yard, and I see lots of trees out here, but a lot of times you don't pay attention, like, wow, that tree is really tall. I wonder how much carbon that tree is storing or pulling in from the atmosphere. And there are ways to figure that out. But there's a really cool way that I'm going to show you that you can actually measure the height of a tree by just using your mobile phone, using a mobile device. And it's something that's really near and dear to my heart because I helped create it. It's called the NASA Globe Observer. And we'll get into that in a second. But let's continue. Well, actually, let me stop here a second. If anybody has any questions about like the NASA fleet or Earth observing satellites before we actually get into, the specifics about why we should care and why does NASA care about tree height.
Can you hear me? It's Carol. Carol King. Okay, there's one question in the chat that says, how many of the Earth observing satellites share information with international partners? And I would say that the person who's asking the question is had a career with NASA himself here in Hampton.
All right. Oh, so at Langley, great. So yeah, so all of the mission, all the NASA data is internationally accessible. It's all free data. Anybody's free to access it. And as on Earth, this is nothing new. There are some countries out there, that are very competitive and aren't very friendly with the United States, and these are NASA missions here. So there's some, satellites out there that aren't, I'm sorry, some countries out there that aren't very friendly, to what we're doing, and they want, to see our stuff. Yeah, that's great and everything, but there's always some weird little, fine line of demarcation between, being friendly and unfriendly with us. So, but I should say all the data, since these are NASA satellites, all the data is freely accessible because it's all paid for by, the American taxpayers. So it's all, and the data, when it comes out, it doesn't always come out at the same time because, depending upon how complicated the data processing is, for instance, like ICET-2, you'll learn in a second that ICET-2 uses laser pulses, whereas like a satellite like Landsat uses basically a camera. So it's a combination, and like SMAP uses radar. So they all use these different instrumentations and technologies where they require certain processing time. The more complicated, the longer the processing time. It's called data latency. So it's one of these things that, once the data is, decided that it's valid data, and that's done through a lot of rigorous testing and the writing of algorithms to make sure that the data makes sense, and then the data is put out there for, internationally. It's put out there, anybody can grab that data. So great question.
Okay, that was it for now.
All right, thank you. So why is tree height so important, and why does NASA care? And basically, why should you care? And I'm going to throw a couple facts up here, some things that I like to discuss. Tree height is the most widely used indicator of an ecosystem's ability to grow trees. Okay. Now, as master gardeners, that's probably, pretty self-explanatory, but I like to think of it this way too. Think about two major ecosystems. Think of like the Amazon rainforest for one. Amazon rainforest, lots of trees, right? Why is that? Lots of tall trees too. There's short ones too, small vegetation, underlings, lower canopy, lower vegetation, lots of things like ferns and all these, exotic tropical trees and plants and shrubs and vegetation. But the ecosystem in the Amazon rainforest is ideal for growing trees because it has really rich nutrient soil like humus. Okay. It has a great climate, has, steady precipitation, and the location, near the equator is, super conducive to all these things. Conversely, if you think about the Sahara Desert or Death Valley, not the greatest places to grow trees. Okay, yeah, there are some things there, like there could be cacti. There are, places, like Joshua trees that grow out there in the, those climates. But there you have, really sandy soil, and sandy soil does not allow the percolation of, water in a, say you have a rainstorm, you get a lot of flash flooding in the desert if you have a, a freak rainstorm, because the grains of the sand are packed together so tightly, they're so dense that you can't get infiltration and percolation of the precipitation fast enough, so you get a lot of flooding. So therefore, not a great place to grow trees. The climate is hot and arid, so it's very uncomfortable. Not a lot going on. The precipitation is usually very low in these areas, and the temperature is super hot. So yeah, so not a great place to grow trees. But look at those ecosystems. The one that has the ability to grow trees, the rainforest. That's a great indicator that is a healthy ecosystem, because when you're looking at these tree heights, where you have these areas with all these really tall, high trees. Think about the sequoias and the redwoods in the northwestern part of the United States. This is great area to grow trees. The soil is very fertile. These massive trees growing taller than basically any other trees on the planet. So yeah, really, really amazing place to grow trees. Tree height allows you to track the growth of trees over time. And what's cool about this is that everyone, I'm sure every one of you on this webinar here, every one of you has some relationship with a tree at some point in your life. You may have, planted one when you were a child, or you planted one recently, and you've been seeing it grow just over time. Maybe not day by day, but month by month, year by year, you've seen this grow over time. And just looking at the height of it is just so simple a concept. Looking at the height of it allows you to track the growth of the tree, right? If you're looking at the tree, for instance, I'm looking out my window again, and I see we have a driveway, and equidistant on either side of the driveway, we have 2 crepe myrtles. As you know, they're big around this area. We have 2 crepe myrtles. We planted them at the same time, and when we got them, they were each about 2.5, 3 feet tall. Now there's one that's about 15 feet tall, and the other one's about 9 feet tall. Okay, and so we were like, we've been tracking these. Why the heck is one growing faster than the other? And it gets more blooms on it. It's wider in size. It expands out further. But then I thought to myself, well, dummy, you're a scientist. Figure it out, right? So I was paying attention to it, and I realized that, oh, duh, the one tree that gets all the sunlight is the one that's growing fastest. It gets about 4 to 5 hours more sunlight during the day, where the other one sits in the shadow of our house, for that time frame, for those 4 or 5 hours that the other tree is getting all the sunlight. So that really, it's kind of a cool unintentional science experiment, because the one tree, the growth is a little stunted. It's very healthy, but it's just the growth is stunted because it gets about 4 to 5 hours less sunlight than the other one, than its sister tree across the driveway. And they're both equidistant, from the sides of the driveway. They both get the same amount of runoff, because it's kind of pitched in the middle, and then it brushes off to the side. So any water that runs off the impervious sidewalk surface, it runs over into those trees and into the root system. So it's not the water, it's just the sunlight that did it. But we've been tracking that over time, is what I was getting to, tracking it over time. And then by looking at it, we're like, hey, wow, we need to figure out why one's growing faster than the other. Science-wise, this is probably the most important thing about tree height, is that tree height observations can help researchers understand gain or loss of biomass. Okay, so basically how much mass is within a particular tree or species, or an area, like an environment. But what we can do from tree height is that, and that biomass information, we can figure out how much how much carbon each tree or a forest or a wooded area is pulling in from the atmosphere, photosynthesizing that carbon dioxide and converting that into oxygen. And then also storing in the tree. The larger a tree, the more carbon is being stored in that tree, or in science terms, that's where the carbon sequestration, the most of the carbon sequestration is. It's being sequestered in the tree's branches, in the roots, in the leaves, in the trunk, all these things. So at NASA, we have missions that are able to measure tree height from space. One is, I mentioned ICET-2, and I'll be talking about that on the next slide, or coming up in a couple slides. And we also, on the International Space Station, we have one called JEDI, and it's the Global Ecosystems Dynamics Investigation. So it's actually looking at basically the tree canopies at the mid-latitudes, like the rainforests and things that I told you about. You know, whatever the path is of the International Space Station, that's the path of, you know, where the instrument can measure the tree height. And by getting this information from space and by getting ground-based observations, which you can become a part of, you know, very soon, you know, actually starting, well, anytime, but we actually have a challenge starting next week. You can just take tree height observations from anywhere you like, where it's safe to do so. And that you have, I always have to say this, that you have permission to access that tree. So now, one of my colleagues here, Dr. Nancy Glenn, she actually works on the ICET-2 mission, but she is an adjunct professor at the Department of Geosciences, and she's also the director at the Boise Center Aerospace Laboratory at Boise State University in Idaho. And she's a really great proponent of looking at the satellite data and comparing it to data on the ground, right? We have access to all this awesome satellite data, but how do we know it's right all the time? You know, yes, it's highly technologically advanced, you know, there's been a lot of testing going on, but nothing is a perfect system, right? So this is one way, you know, these ground-based observations, and you'll see what I'm going to play this quick video here in a second, but she uses really sophisticated ground instrumentation. And you can see here on the left where she's looking up at her instrument, but she combines the NASA satellite data with her instrumentation, then also the citizen science data that comes from the GLOBE program, which I'll mention. But let me play this quick video. This actually talks to you about why citizen science is important and why these ground-based measurements of tree height is super vital for us for understanding, you know, what's happening with our planet's trees.
Measuring tree height because it's an indicator of the environment. And so in this plot, you see very detailed measurements of trees that we're making. But just really general tree height measurements can be super helpful to us. And that's where we're hoping that you'll be able to contribute. So we make these detailed measurements with a terrestrial laser scanner, and it looks like this 3D point cloud over on the right-hand side and in the previous slide. And from those measurements, we track how the trees are changing with time with these increased temperatures in CO2 from these plots. But we're upscaling that with NASA assets, airborne as well as satellite-based measurements. And the more tree heights, the better.
So yeah, that's one thing that I like to touch on, is that she said at the end, the more tree heights, the better. And that's something called data density. And with NASA and all researchers around the world, you know, even student researchers who I've been working with from different countries with the GLOBE program and through NASA, is that data density is super vital because it allows us to build a much more robust data set, and it helps increase the accuracy of the measurements. If we have a satellite measurement of a tree over, let's say, you know, somewhere in Virginia, let's say like somewhere in Fairfax, all right, that there in Fairfax, there is a group of trees that ICET-2 measured. And then we have folks go out there and take multiple measurements of those trees. When we go and look at that, we can combine and compare all that data to try to figure out what how do they compare? How do the ground-based ones compare to the satellite? And are they matching up? If they're matching up, that's amazing, okay? If they're not matching up, you know, why is that? Is it user error, you know, from the citizen scientists, or is there a malfunctioning satellite? An instrument on the space station? You know, that's just one thing that scientists need to figure out. They need those multiple data measurements to help that, because as you know, there's a lot of scientists in the world, you know, professional scientists like Dr. Glenn, but it's impossible to go out and measure every tree, right? Impossible. You know, even every citizen scientist on the planet, if they were going to go out and measure trees, there's no way they could hit, you know, 1 trillion trees on the planet. There's no way they could do it, right? Just be impossible. But we try to get as many as possible. And you'll see here in a second that, you know, we have ones coming from literally all over the world.
Asia.
So I want to show you this video. This video runs about 5.5 minutes, but it's so worth it. It's just one that we released, and it's basically talking to scientists, and it starts off talking about the importance of cryospheric research. And what that is that's just studying the poles. That's studying climate change. And then it sets the precedence of, in order to understand our planet, if we understand trees and how our planet's functioning, how the trees' planets are functioning, we have to look at other parts of the Earth in order to get that bigger picture of what's happening. So it's going to start off with my good friend and colleague, Dr. Nathan Kurtz. He's at the Goddard Space Flight Center. He's the deputy project scientist for ICET-2. And I actually, mentored him when he first came to NASA in the mid 2000s, I think he came around 2006, 2007. And he's going to talk about his work that he's done on basically these Arctic ships, ones that he's been out in the sea ice, and they climb out onto the ice and take observations. And then it lends itself really good to transitioning into, this is how we study our planet as a whole. And now let's focus a little bit on trees. So hope you enjoy this video. And this is a really great video. And like I said, it was just released as a major NASA press release just about a month ago. So it's pretty new, and it's been pretty popular. So let me start it now.
For me, I've only done airborne field work, which is very different than being on a ship, and where it's just very isolated. Like, that ship is really your whole world, and all those people on the ship are your whole world. And then outside the ship is this just very hostile landscape. It's cold, there's polar bears, there's water that can open up underneath your feet. And so it was a very interesting experience to be on the ship, which was very safe and warm and felt good. But then we'd go out and we'd do our field work, and we'd set things up, and we'd be out on the ice, and you could feel like this is a very wild environment. As we were transiting through the ice, we were searching for a suitable ice flow, something that was thick enough that could support us working on safely and also survive throughout the year. While searching for that flow, we had different satellite tools that we were using that would identify the shape of the flows. We could see how big the flows were, but what we didn't know was how thick they were. We went to some of these flows and we found, though these are really thin, we can't actually use this flow. We looked at some ICET-2 tracks in hopes that some of the flows that we had identified, we could see how thick they were. It didn't work out this time, but for a future expedition, I think we've identified ways that we could utilize ICET-2 or something like ICET-2.
While there wasn't enough ICET-2 data for MOSAIC or the multidisciplinary drifting observatory for the study of the Arctic climate to use, Dr. Nathan Kurtz and the team were able to locate an area with the right amount of sea ice thickness by using different methods. Likewise, scientists often use various methods to measure other aspects of our planet, like forests. So why take measurements of the same thing using different methods? And how does measuring sea ice thickness relate to tree height? Let's take a closer look at the Ice, Cloud, and Land Elevation Satellite, or ICET-2. Its main purpose is to measure ice thickness using its sole instrument, ATLAS. But it also measures tree heights as it orbits Earth. This is done with photon counting lasers and algorithms developed to differentiate what environments they are measuring. An algorithm is a step-by-step procedure for solving a problem, usually a mathematical one, in a limited number of steps. Claudia Carabajo was the deputy lead for the Flight Science Receiver algorithms, one of many subsystems of the ATLAS instrument.
The algorithms that process the data on the ground for ICET-2 are tailored directly to address that characteristics of the surface. So they are tailored to sea ice and vegetation. The coherence of those photons when reaching those surfaces changes, so the algorithms need to be specifically tailored to the surface type. Of course, comparisons against other data sets help you, and sometimes you need the help of an additional data set as you're processing.
When I was on MOSAIC, we took specific measurements that are useful and will be used by combining multiple measurements together. We're able to quantify and see whether ISAT-2 is making its measurements accurately and how it's needed to be done.
The ways that you can actually figure out if ISAT-2 is actually measuring the right thing is to compare it with the observations that are being collected by other means. For example, airborne campaigns, other satellite data, and see what the surface looks like. You can look at how things are changing in different seasons.
Whether it's sea ice thickness or tree height, comparing data collected by different missions and field campaigns allows scientists to better understand how the instrument works. Dr. Laura Duncanson uses LiDAR data to create 3D maps of forests, and Dr. Nancy Glenn is currently looking at various ways in which tree height data collected by ISAT-2 and globe observers can be utilized. For both, tree height data adds to our understanding of Earth's systems.
Of course, we can't go out into the woods all over the planet and measure every single tree on the ground. So for ISAT-2, these estimates of tree height, we don't know exactly how precise they are or how good they are in all of the different forests around the globe. There's a lot of variability in forests.
Just like how taking field observations and airborne data collected of sea ice thickness can act as supplementary data to ISAT-2, tree height measurements collected in the field can also be used to do the same. This supplementary data can help scientists account for variability between different environments when looking at measurements collected by satellites. As mentioned, tree height measurements can be taken in different ways. One method is to use trigonometry to estimate the height of a tree. This is the method that students and citizen scientists use. By measuring the distance to the tree, along with angles A and B, using a handheld clinometer or the one built into a smartphone, observers can calculate the height.
Having people go into the woods and actually measure tree height to compare to the satellite estimates of tree height gives us a sense of how reliable those tree height estimates are, and maybe some ecosystems that they're particularly good at doing tree height or particularly challenged doing tree height.
And now we know that by taking measurements of the same thing, using different methods can help scientists. Taking tree height measurements adds a whole new data set for satellites and instruments such as ISAT-2 and JEDI to compare with. These measurements also provide content that only an observer on the ground can provide, like recent changes, including drought, fire, invasive species, and more. Now that leaves the question, why do scientists study trees?
So for decades now, we've had really good maps of where there are forests and where there aren't forests, but we've never before known how tall the trees in those forests are. And this is a really critical piece of information because it tells us not only, of course, how tall the forests are, but how much above ground woody carbon they store. Forests represent one of the biggest carbon stocks on the Earth's surface. And if we cut down and burn forests, we essentially are pushing more carbon into the atmosphere. And if we allow those forests to regrow, we're sucking that carbon out of the atmosphere. But we don't know right now how much carbon is where in Earth's forests because we've never had that third dimensional measurement of Earth's forests, which is so tightly linked to its carbon content.
Using tree height not only helps scientists track how much carbon is getting released into the air, but can also be used in other ways.
Tree height is really important for us is that we're interested in knowing how tree height is affected by increased CO2 or increased temperatures or decreased temperatures. And that gives us an indicator for making predictions about trees in the future. We're interested in is that trees and the differences in tree heights provide some level of what we call structural diversity. And structural diversity can be really, really important for a health of an ecosystem, as well as provide habitat for a variety of different types of animals. So we're using NASA resources, NASA airborne data, as well as satellite-based data like ISAT.
Many Earth-observing satellites, such as Landsat, can only see a top-down view of Earth. This information comes in the form of two-dimensional images made up of pixels between the size of 30 meters squared to 500 meters squared. But now, with JEDI on board the International Space Station and the launch of the ISAT-2 satellite in 2018, scientists are able to see height added to this top-down view of Earth. By taking and submitting tree height observations, citizen scientists and students can help scientists and researchers, not just by providing measurements from different ecosystems, but by providing a different type of data. What seems like such a small piece to contribute can help scientists across the world.
The Globe Observer tree observations essentially let people all over the world measure tree heights and give us that information where we can't go into every single forest ourselves as a small group of scientists.
From a scientist perspective, but also somebody that participates in citizen science, it's a great intersection. More data, the better. But also the connection, right, is that the connection between scientists and the community, and scientists understanding what's important to our communities and being able to engage and learn from one another.
There is a large part of collaboration between the instrument scientists and everybody working on every aspect of the Atlas instrument, and the mission scientist and his deputy and everyone else in all the universities. Citizen science is really important to get the community involved, motivates everybody to be more informed about the science, and also perhaps motivate a crowd of new scientists.
All of this is important because one, it's the pursuit of answering questions about our natural environment. Our natural environment is changing very rapidly.
A tree height measurement that's taken by citizen scientists could be useful for us.
It's really important for us to monitor what is here now so we can document that, but also use that in models to predict what might be here in the future.
To learn more about Globe Observer, check out the website at observer.globe.gov and download the app to start taking your own observations today.
I hope you enjoyed that video there. It's a really good one because it really goes through the importance of not just understanding a small part of our planet. It's how to look at the different variables and observations on our planet in order to paint that larger picture. Everything from that synoptic view we get from the satellite all the way down to the ground-based observation. With the satellite, we're at the top looking down, and the ground-based citizen scientist observations are looking from the ground up. So we get that bigger picture. So let me, I'm going to talk a little bit about ICESat-2, and then we're going to get into, how you can become part of this by taking tree height observations. So ICESat-2 is the Ice Cloud and Land Elevation Satellite 2, and it uses what's called an onboard laser altimeter system. And as you know, an altimeter is an instrument used to measure height, okay? So it's used to measure height. And what ICESat-2 does is it fires laser pulses to the planet, down to the planet, and we calculate the time it takes the laser photons to leave the satellite, which is flying at about 300 miles above the Earth's surface. It's a near polar orbit, so it's going around the poles, north to south, south to north, at about just over 15,000 miles an hour. But when it fires these laser pulses down, we're calculating the time it takes the photons to leave the satellite, to bounce off an object on Earth and come back to the satellite. Now, you don't have to be concerned about it because, we talk about how bad laser light is for your eyes. I like to think of it this way. Think of it as if you have a flashlight and, say 1,000 lumen flashlight, and you're standing in front of someone and they turn the flashlight on and shine it directly into your eyes. It's going to hurt. It's going to be very bright. But let's say somebody walks 300 miles away and turns on that same flashlight. One, you're not going to see it. Two, it's not going to have any effect on your eyes. So that's what's happening here. So as this photon, as the photons leave the satellite, these laser photons, yeah, they're super bright and super powerful, but they spread out as they travel those 300 miles down to the Earth. And as you know, they're traveling pretty fast. They're traveling at the speed of light, since laser is light. By the time it hits the ground, that single point photon spreads out to about 14 meters in diameter, and it's super low resolution. So, it's not bright at all. So what happens is that basically what happens here is when that photon bounces off, say, a group of trees or even an individual tree on the ground, that measurement, that height measurement of the trees is the average of whatever amount of trees was in that 14-meter diameter footprint. So let's say that there were, the photon comes down and it hits a group of trees, and there's 25 trees that fall within where that photon hit. So the height that's coming back is going to be the average of all 25 trees that that photon was able to measure. If there happens to be just one tree in that 14-meter diameter footprint where that photon hit, just a single tree, the tree height that's going to be returned is just the tree height for that one tree. Makes a lot of sense, right? You know, it's going to measure everything that's within that, you know, in that footprint. So lasers, the scientific term for that is called LiDAR, and it's light detection and ranging. It's basically the active remote sensing technology. That's the laser version of radar, and you all know what radar is, okay? Like, you know, a police officer trying to see if you're speeding down the highway, or, you know, a baseball pitcher wants to know how fast he can throw a pitch. You might have been to baseball games where you see a bunch of, you know, scouts, baseball scouting agents sitting behind home plate, you know, with these radar guns trying to find out how fast these minor league pitchers are throwing, you know, their fastballs, you know, to possibly, you know, draft them into the major leagues, things like that. So yeah, so this is what ISAT-2 is doing. ISAT-2 is cool. What you saw here in this video is just showing an artist's rendition of once we got the satellite into space, it has to go through all these things like deploying and opening its solar panel, and then all the instrumentation has to turn on. And then once everything gets set up, basically this door opens up and it starts firing these laser pulses out. Now these laser pulses fire out at 10,000 times per second. And in each laser pulse, there's approximately 300 trillion photons. So of course, because lasers are light, we won't get back all these photons to the satellite, right? Because light can get scattered, absorbed, reflected, refracted. You know, clouds are really thick clouds, and like thin cirrus clouds with ice crystals are a bad thing for ISAT-2 because they absorb the rain droplets. The clouds absorb the light, and then the rain droplets can refract the photons in different directions. The ice crystals can refract the laser pulses and photons in different directions as well. So they're not going to return back to the satellite in the straight line that we're hoping them to do. So out of 300 trillion photons that we send to the planet with every laser pulse, we get about a dozen back to the satellite on average. Doesn't sound like a lot, which it's not. 12 photons out of 300 trillion, that's a huge difference. But think about this. We're firing off 10,000 laser pulses per second. So that still means that we're getting 120,000 points of, you know, verifiable data every second. So since ISAT-2 was launched on September 15th of 2018, we have over 8 trillion photons that have returned back to the satellite. That is a massive number. So we have 8 trillion. You know, if all 300 trillion photons would return, we'd have just an obscene amount of data that we wouldn't know what to do with. That would be almost impossible to store and, you know, and analyze. And that data latency would be unbelievable. So that's what I'm going to focus on here, because ISAT-2, even though it focuses, which you saw from the previous video, it focuses just, you know, its primary objective is looking at ice and how the ice is melting at the North and South poles. But there is a huge component here. Since it's an altimeter in space measuring the height, we can measure the height of trees. So this is that whole thing about the footprint that I showed you, the 14-meter footprint. So ground-based tree height observations, how can you do it? You know, I talked a lot about the satellites, but how can we do it on the ground? Okay, we don't want to make it this complicated. This is all the trigonometry like you saw in the video. There's lots of good science and math that goes into taking ground-based observations. You know, so how can you do it? We don't want you to do it this way though, all right? This is a photo from the late 1800s of gentlemen who are actually working to basically prune a large tree. And this is not the way we want you to measure tree height. We don't need you to climb up to the top of the trees like this and, you know, hang from ropes. And, you know, that ladder just looks very, very dangerous and sketchy. And there's someone standing on top of that ladder. So, yeah, this is just one of my favorite pictures I've ever found on the internet. And it's just mind blowing that the people were this brave, you know, at all in the history of our planet. You know, this is just amazing stuff. So please don't do it this way. So one way we can do it, the GLOBE program has something called a handheld clinometer. And this is something that students have been working with since 1995 with this program. And it's basically, you use the math that I mentioned earlier, but you build a nice clinometer where you have this protractor on here, and you use a straw as a line of sight, and you use a string and a washer or a nut to, you know, to serve as to try to figure out the angle that you're looking at the top of the tree through this straw. And then when you do that, whatever angle you get where the string is swinging when you're looking at the top of the tree. It's a combination of figuring out the tangent of that angle, and then also figuring out the distance from where you're observing the tree to the base of the tree. And that's something that we have programmed into what's called the NASA Globe Observer Trees tool for citizen science. And it's something we built into the phone where you can just use your phone's camera. It's all free, by the way. I'll mention that ahead of time. It's all free. And the only thing you need to do is send an email to, when you go to the app, you can just Google the NASA Globe Observer Trees tool, and you can find out, there's I have some website links on the end here, but you can it'll show you exactly what you need to do. You sign up with an email, you get an email back saying, hey, good to go. Let's go out and take measurements. So then for each one of these things on the NASA Globe Observer, there's also, a protocol to measure tree height. Okay, that's the tree height one. You can do clouds. You can look at mosquito habitats, and you can also do land cover as well. So here's a little promo here about the trees tool, why it's so super important, and why I've been mentioning ICESat 2 previously. So that was just a little promo about about this. So, how do we measure the tree height as a citizen scientist? Let me pause here a second to see if there's any other questions, because this is going to be the last part of the presentation. I'm going to show you, it's a video of me actually taking a tree height measurement. Then I'm going to show you a screen capture just so you can see what you need to do, in order to do this. And once you get used to doing this, then it doesn't take long. You can do a tree height measurement in like a minute or two. So it's really, really easy to do. It's really simple to do. But there's a couple things I want to show you that are super important and vital if you're going to get an accurate measurement. And I'll talk about that in this video, but then I actually have a screenshot I'm going to show you. So let me pause here a second as well.
Yeah, so Brian, the chat box has, it's not really a question, but apparently Bill Blair notes of Gloucester that they are using the Globe Observer slant trees now when they visit homeowners that have questions about their trees. And another question, part of that was they're using visible spectrum instead of IR. Bill, or do you want to talk to that a little bit?
Well, what I do when I go out, some of the basic information we need to know is how big is the tree, and when we're looking at its sizes, and before we start looking at diseases or insects or whatever. So I just generally start out by figuring out what is the tree, and I use this global observer. We got it originally to use it for clouds. Yeah, because we were teaching weather to master naturalists, and we got the observer to use for clouds. And then all of a sudden I realized, hey, not only are we giving data on clouds, but this tree thing really works and makes it so easy. I mean, I don't have to pull out tape measures. I don't have to, guesstimate. I don't have to get my cell phone out to do the calculations. It does it all for me, and it's so easy. And I hope you're going to show them exactly how to do it, Brian.
Yeah, I will. Hey, I don't even need to give any more of a presentation. You just did an awesome pitch right there. That was great. I love that. That makes me so happy to hear that you're using this for this. And that's really cool, because we always like to hear from the citizen scientists and the people who are actually using it and what they're using it for. So that's just great information. I'm definitely going to share that with my colleagues as well.
Well, and the beauty of it is it not only solves our problem, but every time we do it, it's another tree into the system that can be used by you all. Yep. And it just keeps adding it up and adding it up. I do it also when I go out with the Forestry Service, and we're doing our measurements out there and some other calculations we're doing for homeowners who have forestry plots and they're trying to decide what they're going to do and how they're going to expand them. We use it for measuring that out there too. So it really works out pretty good.
That's excellent. Yeah, that's what I'm going to show right here. I'm going to show, this is me. It's going to be me. This is, this was actually, when did I take this? I think I took this March of last year, but it's looking at a really nice Bradford pear tree that actually was, half of it was destroyed during Tropical Storm Isai in last August. But I'm going to show you here, and I'm going to run this. I'm going to play this video. I'm going to run this through, and it's going to show you exactly, all about how to take a tree height measurement. And hopefully you learn a lot from this video. But I'm just going to show you this, and then as I mentioned, after this, I'm going to show you the last part of the thing about, I'm going to show you a screenshot what you're actually going to see on your mobile device when you take a tree height observation. Here we go. Oh, sorry, wrong one. That is the same one. Sorry, it's this one. All right. So here we go.
Hi, this is Brian Campbell of the NASA Wallops Flight Facility. I'm the tree science lead for the NASA Globe Observer. Today, I'm going to talk to you how to take an actual observation using the NASA Globe Observer Trees tool. So in order to get started, you first have to go through the introduction. In the introduction, it will ask you for some very vital information. You have to input your height. And if you input your height, what the app will do is it will then estimate the eye level of your phone's camera from above the ground. And also it'll estimate your stride based on that height. You also have to determine if you're going to use the metric system or the English system in your observations for the units for your tree height measurements. So what we're going to do is we're going to get started taking this observation. Before we do any of this, I want to make sure that you're aware that in order to do this the way you should be doing it, you want to be able to do this safely and legally wherever you are. If you happen to be on private property where there's a tree, make sure you get the permission, but you want to make sure that you do this safely and legally and follow all local jurisdictions and laws in your area. So let's get started. So we're going to go into the trees tool and we're going to just go click trees, new tree observation. And what you get, you'll get the time, you'll get a date stamp, time and date. Make sure that's right. And then what it's going to do, it's going to ask for service conditions. We want to know what's happening around your local environment when you're taking the tree observation. Meaning, is there snow or ice on the ground? No. Standing water? No. Is it muddy? No. No dry ground. There are leaves on the trees and it's not raining or snowing. So then once you do that, you're going to measure the base of the tree. So this is really cool because you click next, measure base, and your camera will open up. And you're going to make sure that your phone's camera is always at your eye level. So keeping it at eye level, I'm going to go to the base of the tree and I'm going to align this line, this white dotted line to it. There we go. It's at the base of the tree. I like that. I'm going to continue to measure the tree top. Keeping it at eye level, you're just going to angle the phone up to the top of the tree. And there we go. We're at the top of the tree. We got the top of the tree. So what we're doing is we're measuring the angle from your eye level to the base of the tree and the top of the tree. And the phone your phone uses the internal magnetometer and the app uses that information to calculate these angles in order to get you to measure the actual height of the tree. So we have the base and we have the top. Now we want to take a picture of the tree. And this happens to be a really pretty Bradford pear tree. So we're going to click on that and it takes a picture of the tree. Now, since I'm on a flat surface, what I'm going to do is I'm going to walk normally to the tree. Okay, and you should ultimately be about 25 to 75 feet away from the tree. I'm about at 25 to 27 feet away from the tree. But as I walk towards the tree, I'm going to walk normally. That's super important, to walk normally to the base of the tree. Normal steps, because that's what the app based your stride on with your height that you input into the introduction section. I should also mention that there's a tutorial section in the app that you need to do before you start, so you can learn exactly how to do the tree height observation. But now I'm going to walk to the tree, and I'm going to walk normally to the tree, normal steps, counting my numbers out loud. So here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 18 steps. So you input that into the box, 18 steps. Now, what it's going to do is it's going to go to the location. It'll give you the latitude, estimated latitude and longitude of the tree. Okay. It'll tell you what you think, what the app thinks your estimated accuracy is. And if you like it, you can hit set position. But if you don't, what you can do here, you can go to a map. And this map, you can move with 2 fingers and say exactly where that tree is. Okay. So I think it's right about here, okay? So once I set it, I hit set position. Then you're going to come to a screen that says circumference. If you have a tape measure available, you can then take the circumference of the tree at breast height, about 4.5 feet above the ground surface, all right? Now I should also mention that since we did it this way, we're on a flat surface. If you happen to be on an area that's very sloped, like you're walking uphill to the base of the tree or you're walking downhill to the base of the tree, what you can do is you can pull out that tape measure, and from where you took the observation from originally, you can measure the exact distance from the location of where you were standing to the base of the tree. And then you can put that information, excuse me, in this section. The section here is the review section. It gives a camera height, the stride length, the number of steps you put, distance to the tree, and then in the yellow section, the calculated tree height. And if you don't like something in here, or you took the actual measurement from the base of the tree, from the location where you're standing to the base of the tree, you can hit the edit button and you can put that distance to tree right in here. So once you do, you just hit finish, okay? So then all that information then will be sent to the GLOBE database, where researchers, student researchers, professional researchers, and citizen scientists can access that information. So I'm going to send my trees data now, and it's being sent to GLOBE. And then there are places on the app that you can go look to see where you actually took your tree height observations. So before we finish, okay, that's the actual tree height observation, okay? But before we finish this little clip here, a couple things I want to focus on to make sure that you remember is that you always want to keep the phone at eye level when you're taking the measurements, okay? So always at eye level. That's the most important part, because if you look at the base of the tree and you go like this, or you go to the top of the tree like this, you're changing the angle at which you're viewing the base and the top of the tree. An important thing to remember is that if you have multiple people taking observations using the same device, what you need to do is you need to change the height of the observer each time, because we're assuming that they're going to be of different heights. So if they're of different heights but using the incorrect height, the tree height observation will be incorrect. It'll be an erroneous tree height observation. So how you can remedy that, when you go into the trees tool, there's a little question mark. That's the help section. You click on help and it says change current user height settings. So when you can do that, you can go right in and change the height of the observer about to take the observation. So hopefully all this helped you in understanding how easy it is to take a tree height observation using the NASA Globe Observer Trees tool. Have fun using the NASA Globe Observer Trees tool, and thank you for all your vital tree height observations.
All right, so let me quickly do this because I know our time is just about up. But I want to show you this. I'm going to run this here. This is what you're going to see when you go into the app. So this is, I'm going to go in here and I'm going to click on trees and I'm going to click on new trees observation. Now I'm going to have a bunch of different things here. You probably won't see all this here, these organizations. These are things that I work with. But here's this timestamp that you get. And then here are these surface conditions that I just mentioned in the previous video. You want to look around you and answer these simple yes/no questions about the environment. And then when you're looking at your tree, when you're about 25 to 75 feet away from the tree, you're going to align, remember keeping the camera at eye level, align this to the base of the tree. And then if you like it, hit yes. And then you're going to do the treetop. Without moving your arms, you're just going to tilt your hands. See, I didn't like that one, so I'm going to try again. And then I like that. And then I'm going to take a picture of the tree. So all you do to snap that, this is all you need to do to just get this is just press on the screen, okay, to get that screenshot. And then you can take a picture of the tree, and this will get sent to the Globe database as well. And then you're going to walk to the tree, counting your steps. You're going to walk in that normal stride. I'm going to fast forward a little bit to get to the next one. So once you input those numbers into those steps, you're going to go to the next thing that you're going to hit is this location that I mentioned. It's going to give you what the app thinks your latitude and longitude is. And then there's a map on the bottom that if you don't think the red arrow is lined up to where your tree should be, you can move it by putting 2 fingers on the map. And that's what I did here. And then I went and took the actual tree circumference. This took a while, so I'm going to fast forward this. It took a while to measure that because I was there by myself. Didn't have someone there helping me. But then I found out what the tree circumference was. And then I go to this most important review step here, where it gives you your camera height. Now, in the introduction section, as I mentioned, where you put your height in, the app is going to estimate your eye level to be about 4 inches below the top of your head, basically 4 inches below your height. And then it's going to estimate your stride length based upon your height. And then the number of steps that you input, and then it's based on those number of steps, your stride and your camera height, it's going to figure out the distance to the tree. And then in that yellow shaded area will be the calculated tree height that you get on the app. And then the circumference as well, if you decided to do that. That's an optional observation and measurement. Now, the comment section is really important because it allows you to put anything in there about the tree that you notice. You might want to, if you notice what type of tree it is, you might say it's a deciduous or coniferous tree. Or if you know it's a maple tree or, a saucer magnolia, or a cherry tree, or a Bradford pear, or a crabapple, or whatever, you can put that information in that. That's called metadata. So once you do that, you get that information, and if you need to change anything, you're just going to click on that edit button, and then all these will open up, and you can change anything you need in there if it doesn't look right. And then once you do, you're just going to send all your observations, and then that goes to the Globe database. So here is where all the data is coming from. These are all tree height observations coming from the NASA Globe Observer. Over 45,000 tree height observations from 18,000 global locations. So each picture that you see here is an individual tree observation. You can see the ones on the top are from the United States. On the bottom is, the entire world, through the Globe program, with citizen scientists coming from these 125 countries that are participating in the Globe program. So how do you become involved? And this is you can do it at any time. But we have something called the 2021 Community Trees Challenge starting next week next Thursday, April 15th. And it's going to run for an entire month to May 15th. And basically what this is through the Globe program at NASA, it's basically an intensive observation period where we want to try to get as many observations as we can in this month-long period. That helps us with many things, to get the amount of data in the database that we need for scientists and researchers, students to use for their research projects, but then also to help out with that data density issue, to try to get as much data as we can to help compare it to the satellite, to help us understand that carbon content, the ecosystems, and the whole pulling in carbon dioxide, storing it, converting it to breathable oxygen through photosynthesis and all these things. But we understand that some people may not be able to go out and take tree height observations. So we created, as part of this trees challenge, this community trees challenge activity tracker, where you can go into the website, and I have a link here in a second. You can go to the website and learn all about trees. You can learn about why trees are important, why land cover is important, because land cover is, trees are a part of land cover, right? So we understand why land cover is important. It'll help you understand why trees are important and all the different activities you can do. Maybe you have grandchildren, or children who want to be able to learn more about this stuff. They can go in and watch videos of trees that we've created, different activities, from, artistic ones, writing tree puns or poems or songs, going out and taking an observation, how to make a video, looking at the tree science on social media, all these things. So we wanted to provide a combination of, the ability for people to, the opportunity to go outside and take tree height observations, but then also have resources available to take their understanding and learning a little deeper, into understanding what's happening with all the trees. So here are challenges to you during this. If you can take a tree height observation, that's great. Go out and do it for as many trees as you can. If you want to take the ones in your yard, just do your yard, but you take as many tree observations as you can. If you take one, you can also, we recommend to take a land cover observation. That's just to simply go back, hit the home button on the app, and you take a land cover observation. You have to go through the tutorial and introduction section as well for that, but you can take a land cover observation. But then as I also mentioned, if it's not safe to go outside, or you don't feel comfortable going outside taking tree height observations, or you don't want to use the app, which we hope that's not the case, there are a lot of other resources that are part of this Community Trees Challenge. So let me flip here through. I'm going to go through here and just show you. Oops, sorry, I went too far. The associated links and contact info for this information is, through the GLOBE program. You can go to the NASA Global Observer Trees tool. Lots of challenge things here as well. So, and then you can learn more about ICESat-2. So I hope today helped you understand. I gave you a lot of information, and that's usually what I do because we have so much to offer. NASA does so much stuff. But I really wanted to tie in the idea of, what NASA does, why NASA has a satellite in space that can measure trees, how it measures trees, and then also how this ties into how citizen scientists tree height observations are super vital, and how you can do it, as your group, the Virginia Cooperative Extension Master Gardeners Program, or any group that you may be affiliated with, or family members that you want to take out and take these observations, or as mentioned earlier, I think it was Bill mentioned earlier, going through people's yards, homeowners' yards, and figuring out how tall the trees are in your yard for different purposes. So I think that's, we like to hear that type of thing. So here's my email if you want to share anything with me or have any questions. You'll see it on the bottom here, brian.a.campbell@nasa.gov, and feel free to write me anytime, and we'll connect and figure out what you want to talk about. If you have any questions or comments or concerns about anything trees related, NASA earth science related, or NASA science stuff in general, let me know. So I'm going to go ahead and unshare and go back to the main room because I'm sharing my entire screen, so I only see just what I see on my screen, what you're seeing from me. So let me come back and take any last minute questions or comments or concerns or ideas.
Yeah. Okay. So Brian, wow. The key question here. There are two questions in the chat box. The one that I have several people interested. We are recording this. We just do routinely for people who are not able to attend. I think I mentioned that before. Is it okay for us to share this video with others?
Yep, share away. That's
okay.
all. Yep, share away.
Everybody, so
anybody you can. Yep.
Yeah, and there's a specific question that asks, can you use? Is it okay to put the your camera? I assume the camera on your phone on a tripod.
Yes, you can, just as long as I'm assuming that the tripod has, well,
Because I mean,
What you have to figure out though is you'd have to figure out what the height of that tripod is,
Right.
because wherever that camera is, because the app is basing it on the height of the observer. So if essentially you could, if you'd figure out the height of that tripod, you'd have to put that in. What's tricky about that is that because the height you're putting into the app is a human height, the app estimates it to be, your camera level to be 4 inches below the top of your head. So essentially, if you use a tripod, what you'd have to do is just put in the height of what the top part of that, if the camera's on the tripod, how high it is from the ground to the top of the camera. Okay. And if you put that information in, you'd have to put that in as the height of the observer. But when you go into the actual, that review box after you take the measurement, I should also mention, if you're going to measure the base of the tree and the top of the tree, you'd probably have to have that, the little arm on the tripod to angle the camera, like this, angle the camera, up and down to the base of the tree and to the top of the tree. But when you get to that review box where it asks you, it shows you like your height and all that, you'd have to definitely hit the edit button. And where it says height, you want to put in exactly the height of that, where your camera is on the tripod. Because
wouldn't that affect though the calculation of the normal step length based on the height of the person?
It would. That's where it gets tricky, because then you'd have to probably go in and use the tape measure to measure the distance from the tripod to the base of the tree. So you couldn't really use your steps, and you couldn't use your body's height. So you'd have to change a bunch of things in that edit section. It's possible to do. We prefer it to be a person actually doing it, like holding a phone and not on a tripod, but it's possible, just as long as you change those things in that review section. If not, you're going to get a tree height that's probably going to be off by like, maybe a couple feet to a meter or more, because the angles will be measured differently. So, and that, as you mentioned, the stride, you can't really measure the stride, because it would be actually, whatever height you put in, it would be like, well, that's the stride of the tripod, and that's not what you want to be able to measure. You can't measure that. So, yeah.
So, well, super. So, I don't see any other questions. Anybody got anything they want to speak up to? There's a lot of us out here, but feel free to come up.
I'd like to make a comment with Brian and see what he thinks of this. Brian, what I've done is, because I do a lot of hiking and orienteering and stuff, I have a pace measurement.
Yes.
That I've measured my pace uphill, downhill, and on the flat. And I use that to check so that I don't have to carry a tape measure with me all the time, a long tape measure. I carry my tree measurement, but not a long tray. And I use that just to check. And it seems to be very, very close on the what it calculates and what I've measured. And we do that on a regular basis, because as I get older, my pace gets shorter. But I can attest to the fact that it is a pretty accurate measurement. We tried several times. We would do the paces, let it calculate, and then we would actually measure. And it's so close that it's not worth worrying about.
Right. Yeah, that works. And I'm going to post something here in the blog, in the chat, where it's actually a blog that I wrote about that kind of same thing there, about, if you want to try to figure out what your pace is, and what your stride is, and use that, for something to, so you have that information. So I'm going to put that in here. I'm going to put the link. I just shortened the link to this because it's a really long link on the Globe program. But if if people are there and if you want to copy that down or click on that, it'll open up another window, but it'll be it's basically a blog that I wrote called Pacing, Tree Height, and Land Cover. So it tells you all about what pacing is and what stride is. And then basically it's an activity that we created for the Globe Observer to help you figure out what your pace is. So that's great. Yeah, thank you, Bill. That's definitely really important because, you know, if you're out there doing that, so you don't have to carry a, you know, heavy tape measure in your pocket if you're doing hiking, because, you know, you want to optimize the amount of weight that you have on you when you're taking hikes for sure. But yeah, so you don't have to worry about, you know, fumbling around with a tape measure. So yeah, if you have that stride, and when you get to that edit section, you know, you can actually pop in whatever your stride is, what your particular stride is. If you're, as you mentioned, you know, even if you're walking on a flat surface, your normal stride, but as you mentioned, you know, walking uphill, walking downhill, that you calculated that as well. So, you know, you're out there more advanced than a lot of the citizen scientists are that we've worked with, Bill, as far as figuring out what your stride is, you know, to put in there. But that's great. That's great advice, though. It's a good thing to do.
Brian, if you want to send me that, the link to the blog, I
Yeah,
can
sure.
send an email, then I'll insert that into our minutes. Pass it out.
Okay, excellent.
That's better than putting in the chat box.
Okay, great.
Yeah, super. Well, my goodness, what an awful lot. I can see how excited, why you are so excited. I do hope that there's a huge return next week. It's perfect time, you know, spring is here and everybody's outside. So that is pretty darn cool.
Yeah, we're super excited about it, and we're hoping a lot of people go out and take measurements. I mean, over here in Salisbury, the sun's trying to peek out. It was raining this morning, but it's going to be raining off and on for the next couple days. But we need it. We need it. I mean, we've had a lot of rain here over on the Eastern Shore for, you know, this you know, last summer into the fall, like way too much. It's flooded a lot of the agricultural fields, but it's been a little dry lately, so we could use a little bit extra rain. And with everything blooming, the plants need it now. A lot of them are out of dormancy. So, but yeah, I appreciate the invite, and this is great. I like great group here and great questions, and you know, thank you for you know, inviting me here. And you know, as a member, I'll send and also share on your minutes, Carol. You know, share my email if they want to get in touch with me.
I will
That's
do that.
fine.
And
Yep.
I will also send you, for I'm sure you have, like all the rest of us folks connected to the government, you probably need to report on things. So I'll send you some demographics.
Okay. That's good. Yep. Yeah. Always metrics. You know how metrics work for sure.
Absolutely. Okay.
Yeah.
Super. Yes. All right. Well, you take care. Have a beautiful rest of your day.
All right. You too. Thank you, everyone.
Mm-hmm.